know that then.
So Delacar's really, yeah. So he's going to divide this. All right, welcome back to physics, everyone. So yesterday we started talking about how to actually add capacitors together to create new capacitances, and we said that there are two things, which are series and parallel. And remember, series means that there is one direction that charge can actually flow through the system, which means that there's no options, right? So basically what we want to do now is look at what happens if I have, say, 3 capacitors in series with each other. What does that do to the overall capacitance of the system? So basically, our claim is going to be that we can take these 3 capacitors and then combine them into another circuit, which looks just like this, which is the same thing, but with only one capacitor. So basically, our claim is that these 3 capacitances, or capacitors, act as one simple capacitor, which has what we call an equivalent capacitance. So we want to know then, what is the equivalent capacitance for these 3 capacitors added together? So this is what we want to know. Now, first thing to note is what? Since charge is coming out through here, this positive charge is going to get put onto this plate here. That's going to kick off the positive charge from here, leaving this one negatively charged. Those positive charges are going to go here, kick off the negative charges here, causing this one to be like positive charges from here, leaving this one to be negatively charged. Positive charges are going to go here to kick off the make this one positively charged, kick off the positive charges here, leaving this guy negatively charged, leaving all these guys to go back in. So basically what will happen is this side will become positive, 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 and then all these other ones are going to become negative. So they become negatively charged, negatively charged, negatively charged, and etc. Now, by charge conservation, the amount of charge which moves through this circuit has to be the same at any location throughout the circuit because of charge conservation, which basically means that what the charge on this plate here is exactly the same as this charge on this capacitor here, which is exactly the same as the charge on this capacitor here. So the first thing we learned from this is that in series, charge is the same. So all of these different capacitors will have exactly the same amount of charge because of charge conservation. Now, since this charge here is on this equivalent thing here, so the charge coming out is dictated by the amount of battery as well as the overall capacitance. What that means then is that the amount of charge on this equivalent capacitor is exactly the same as the charge on each one of these individual plates. Now, what is true though is that again, the battery is supplying the potential difference, which means that this guy has to get rid of potential, so it has to be a potential drop. This one also has to be a potential drop. This one also has to be a potential drop. But since they all have different capacitances with the same charge, what that means is each one of these is going to drop a different amount of potential. So this is going to have a V1 drop, a V2 drop, and a V3 drop. But by energy conservation, what has to be true then is the sum of these 3 potential drops must be equal to the amount of potential which is supplied by the battery itself. So this is going to be our starting location. So we're going to say then that the potential supplied by the battery must be equal to the potential drop across the first capacitor, plus the potential drop across the second capacitor, plus the potential drop across the third capacitor. But, again, by energy conservation, the potential drop across the equivalent capacitor must be equal to the potential gained by the battery, which means that the potential here is the same as the potential here, which means I can also rewrite that potential in terms of the equivalent capacitance. Now, also, based on what we talked about yesterday, we know the charge is equal to the capacitance times the potential, which means our potentials are simply equal to the charge divided by the capacitance. So what we can do then is we can rewrite each one of these potentials in terms of the charge and the capacitance, and then rewrite this potential in terms of the charge and this capacitance. So let's do that. So this guy's going to be equal then to the charge divided by the equivalent capacitance, then equal to the charge divided by C1, plus the charge divided by C2, plus the charge then divided by C3. What's true about all those charges? They're all the same, so we can cancel those out. So finally what we get is that 1 over CEQ is equal to 1 over C1 plus 1 over C2 plus 1 over C3, or this is equal to the sum over I of 1 over CI. So this is my equivalent capacitance for capacitors connected in series. So it says that 1 over the capacitance is equal to the sum of 1 over each one of these. Now, what physical effect does this have on the overall size of the capacitance? So if I'm adding things inversely together, what does that do to the overall size of the node? Does it make it bigger or does it make it smaller? Makes it smaller, right? Because here, by adding 1 over each one, then I have to take an inverse of all that at the end of the day. The overall physical effect is that this decreases the overall capacitance. So if I want to make a capacitor whose capacitance is less than the amount of capacitance I have in a single amount of capacitor, then I have to add them in series to overall decrease the size of the capacitance. This is the overall effect. Now, why is that true? Well, this is true because remember that for a parallel plate capacitor, down here, we said the capacitance was equal to epsilon naught times the area divided by the distance. Which means when I'm adding these three in series, what I'm effectively doing is I'm increasing the distance between the plates. Because by adding these together, you can think about it as basically the area or the distance now becomes the distance between the two, which means if I increase the distance, I decrease the amount of capacitance. Overall, the effect of this is from increasing the distance. Increasing the distance between the plates. Good, so this is series. So again, in series, what has to be true is the charge on each capacitor has to be the same. And we're going to decrease the overall capacitance by adding these guys inversely together. So this is in series. Our other option then was in parallel. So let's talk about parallel. Parallel, I had my plates here, connected then to, again, 3 capacitors. Put one here, C1. Another one here, C2. And another one somewhere down here, C3. I'm going to connect all these guys together and run them to the battery. So good. Now again, what defines parallel, just to remind you from yesterday, is these points here. Again, these are called junctions or nodes. And again, at this point, the charge has a choice on what direction it wants to go. So the charge that comes out of here can instead go to this point and then go in this direction, apply itself to this plate, or it can go through here and apply itself in this direction, apply itself onto this plate, or it can go through here and go through this leg and then cause itself to go onto this plate. Which means that ultimately what's going to happen is I'm going to have some of the charge here, Q1, and have some of the charge here, Q2, and some of the charge here, Q3, where these charges are not going to be the same. So again, this side will become positively charged, positively charged, positively charged. But in general, those charges will not be the same because they all have different capacitances. What's up?
Would the charge be equal like the junction?
Correct. So the amount of charge that heads into the junction is the amount of charge of Q. Exactly. And that has to equal the sum of these 3 charges by charge conservation. Exactly. So what's going to happen is the amount of charge coming out of the battery will be the amount of charge Q. And what has to happen then is the sum of these 3 charges must be equal to the charge coming out of the battery by charge conservation. So the charge coming in here will split up into 3. The 3 of those added together must be equal to the total charge. Now, since the charge is not the same, what is the same? Well, what is the same in this case is actually the potential. And the reason for that is, again, remember that from lab, anytime I have a closed loop, the change of potential must be equal to 0. Which means this is a closed loop. I can go through here, go through this leg, come back in this direction, which means the potential added by the battery must be equal to the potential across C1. Or I can go through this leg, through the center, that's also a closed loop, which means that the potential here must be also equal to the potential across the battery. Or I can go through this closed loop here, which means that the potential here must also be equal to the potential across the battery. So what has to be true is in parallel, the potential across each one of the capacitors has to be identically the same. So in parallel, the voltage must be the same. Has to be true. So in this case, what this means is that the potential here is equal to the potential here, which is equal to the potential here, which is equal to the potential here. Now our claim is going to be identical as before. We're going to say is that this whole thing can be brought down to one equivalent capacitor, which again has a capacitance of CEQ. So our claim again is that these three together will work together as a simple equivalent capacitor where we combine those three together in such a way to make that equivalent capacitor. So in this case, we're going to start here. So the total charge must be equal to a constant. So you're going to say, well, the charge is equal to the charge 1 plus the charge 2 plus the charge 3. And again, using that the charge is equal to C times V, I can then rewrite this then as C1 times the potential plus C2 times the potential plus C3 times the potential. But again, simultaneously, I know that the charge coming out of the battery has to be exactly the same charge which is sitting onto this capacitor here, which means that this also has the same amount of charge Q with a potential of V, which means I could rewrite the left-hand side, then it's simply the CQ times the potential V. What's true about all of those potentials? They're all the same. So I can cancel those guys out, which finally tells me then that CEQ is simply equal to C1 plus C2 plus C3, which is then equal to the sum over all the capacitors. What's the physical effect of this? It increases the overall capacitance. So in this case, the capacitance increases. So if I want to have a greater capacitance than any of the capacitors that I have to add them then in parallel to each other to increase the overall size of the capacitance. Physically, why does this happen? Well, this happens because if I look at them and I think, okay, I'm going to line all these guys up and squish them together, what happens in that case is I'm increasing the overall cross-sectional area. So again, if I go back to my parallel plate capacitor, if I increase the cross-sectional area, I increase then the overall capacitance. So the physical effect, or the physical reasoning why this is true, is that we're increasing the cross-sectional area. Increasing the cross-sectional area. So good. So for those of you who are in circuits, you guys have circuit dynamic. You've probably seen resistors. This is the opposite of the resistors. So resistors, you add them together in series, and you add them inversely in parallel. This is just a complete opposite. We'll get the resistors soon enough. What's up there?
What is capacitance measure again?
So again, capacitance is a measure of how much charge a capacitor can store given an amount of potential. So if I took a particular capacitor and I put a particular potential across it, it's basically telling me how much charge I can store onto that capacitor, which is directly related to the amount of energy that it can store. And we'll see that in a little bit. Is okay? So great. So now that we know all these things, our job then is to have things that look like this. So what you're going to be given then is a bunch of capacitors with a battery in a beautiful circuit like this. Doesn't find much uglier than this. And your job then is to find all kinds of different things. So in this case, the only thing we want to do is find what is the capacitance or the equivalent capacitance for this particular circuit. We'll do another follow-up example of this where you have to do more stuff. But basically, you're going to be tasked to do a lot of things. You'll have to find the equivalent capacitance, you'll have to find the potential across each one of the capacitors, you'll have to find the charge across each one of the capacitors, and etc. So basically, what you do in a problem like this is you first have to go through and identify what is in parallel and what is in series. Once you identify what's in parallel and what's in series, you can then start combining these things together using the rules of the stuff that we know to then find the overall equivalent capacitance of the system. So here we're told that C1 is equal to C2, which is equal to C3, which we're going to call just simply C, which is 12 picofarads. Remember, pico is 10 to the minus 12. So in this case, we just want to know what is the overall capacitance for the system. So let's draw our system. Here's my example. So here's my battery. That's attached then to this one, which is the C1, I think. I get all my C's right here. That's here. All that goes to there. like C1, C2. Actually C2, C3, C1, a battery. Okay. So first thing we're going to do is look at what is in parallel and what is in series. So in this case, what's in parallel and what's in series? Good. So C2 and C3 are in parallel. So I know these guys are in parallel. And then what? Good. So then in this case, the combination of C2 and C3 is then in series with C1. Right? So then I know this combination here is going to be in series. Now, the way that we're going to do this is we're going to combine things, but every time we combine something, we're going to draw a new picture. And so eventually we get to our final CEQ. Now, the reason we're going to do that is, as you'll see, when we actually start doing what's the potential across each one, what's the charge across each one, what we're basically going to do is we're going to have to go all the way down into one direction and then go all the way back, unraveling what we just did to find the charge and potential across each one, using what we know about each different case, where again, the charge has to be the same in series and the voltage has to be the same in parallel. These are our key concepts that we have to use through these things. These problems are pretty easy, but they're kind of tedious because the bigger it becomes, the more amount of steps I have to do to get there. But again, we'll kind of see how this works. So first thing I want to do is just draw a new picture. I'm going to say this thing reduces down then to, so here's my battery. And I'm going to connect C2 and C3 together to create a new capacitance C23, which has been connected in series to C1, as Derek told us. Then I'm going to connect these two together into my final, which is then going to be simply my CEQ. Now, C23 came from two capacitors which were in parallel, and how do I add capacitors in parallel? Just add them up, right? So in this case, I know C23 is simply going to be C2 plus C3, but I know that's equal to twice of C, which is then going to be equal to 24 picofarads. I know C is equal to 12 farads. Finally, from here, I know that CEQ came from two capacitors which are connected in series, and how do I add capacitors in series? 1 over, so in this case, then what I know is that 1 over CEQ is going to be equal to 1 over C2, 3, plus 1 over C1, which means that CEQ then is going to be equal to C1 times C2, 3, all divided by C1 plus C2, 3. This inversion. Are we okay with that stuff? So all I did was find a common denominator, which in this case is C23 times C1, which means where this bottom part comes from, and then I just inverted it. Okay? Now be careful with this. And the reason I'm saying be careful with this, because if I had something that looked like 1 over CEQ is equal to 1 over C1 plus 1 over C2 plus 1 over C3, and then you write something like, well, I've seen something similar to that before, so I'm going to write this as C1 times C2 times C3 divided by C1 plus C2 plus C3. This is not correct. Okay, so just be careful. Why is that not correct?
3 terms, not 2.
Good. So in this case, I have 3 terms on top. I have 1 term on the bottom, which means this is a C cubed divided by a C, but what's a C cubed divided by a C? C squared. So I have a C is equal to C squared, but can C equal C squared? No, right? So just be a little bit careful with that. Also, this doesn't work algebraically. So the correct answer to this would actually be C1 times C2 times C3 divided by C1 C2 plus C1 C3 plus C2 C3. Right? This is actually the correct answer, but just be careful. So don't just try to match this to like everything. So just be a little careful with that. So anyways, good. So anyways, in this case, we know this is C, this is 2C, this is C, and this is 2C. So this is going to be the same thing as what? 2C squared divided by 3C, which is the same thing as 2/3 C. So this is my overall capacitance, where 2/3 of C is the same thing as 8. Fine. What's offset?
And you missed the 30%.
Go back. Yeah, C was given as, let's go back to the question. So C was equal to 12. What's up there?
Would this still work? Because series or parallel?
Yes. Yeah. So even if I move this thing to this side, it would still be exactly the same expression. So again, you would just identify what's in parallel and series and then slowly put them together to create something different.
Well, I was thinking because like.
Yes, so the voltages and the charges and everything would be affected, correct. But the overall methodology would still be the same. Correct. Okay? Let's do another example. Good. So this says, in the figure below, we have the voltage is equal to 12 volts from the battery. We have C1 is equal to C4, so this one's equal to this one, which is 6 microfarads. We have C2 is twice of C1, so that's going to be 12 microfarads. And then we have C3 here is half of C1, which means it has 3 microfarads. So what I want to know in this case is simply, what's the charge on that guy? How much charge is on the fourth capacitor? Just that one. So let's draw all this stuff here. And you'll see kind of what I was talking about. So in this case, again, we have our battery. Here's our battery connected then to, so here I have a C1 connected down here then to C3, connected over here to C2, connected here to C4, but I have a bridge point here. I got another bridge here, connected then back to the battery. Okay. Good. So again, first thing I'm going to have to do is start combining these things together by looking at what again is in parallel and series. Okay. Every time I do that, again, I'm going to combine them together into a new picture. From that new picture, I'm going to then draw the next picture, because again, as you'll see in a second, we're going to have to go all the way in one direction, all the way back in the opposite direction to undo what we just did to determine one simple question, what's the amount of charge here? So let's do that. So first of all, what's in parallel and what's in series?
C1 and C2 are parallel and C3 and C4.
Good. So we know these guys are in parallel. This is going to give us parallel here. These two are also in parallel. So this is going to give us parallel, which means we're going to get a C1, 2 here and a C3, 4 here. So let's do that. So let's combine these guys together. So here I'm going to get my battery. Going to be connected now to C1, 2, connected then to C3, 4. And then how are C1, 2, and C3, 4 connected? Series. Good. So now these guys are connected in series. So now I'm going to combine these guys together to give me my final, which is now my CEQ.
So what happened to that bridge point?
I'm sorry?
What happened to that bridge point that's connecting?
Oh, because these guys are in parallel. So when I put these guys together, I'm taking away that bridge and I'm putting it into the fact that they are in parallel with each other.
Oh, that's what makes them in parallel?
Correct. Exactly. Exactly. Because otherwise, so let me kind of work on what Derek was just saying. If I got rid of this bridge point here, and I had something that looked like this, what's now different? Right, so these two are now in parallel with these two, but these two are in series and these two are now in series, right? So what's different now is if I got rid of that bridge point, C1, 3 are in series, C2, 4 are in series, but then C1, 3 is in parallel with C2, 3. Because I still have 2 bridge points. I have one here and I have one here. I still have 2 junctions and 2 nodes. But now I don't have a junction and node here, which no longer makes these guys in parallel, at least with each other. So exactly. So Derek was pointing out, this bridge point here, or these 2 junctions, force these 2 guys to be actually in parallel with each other. Okay? So good. So now, again, our task is to find the charge here. But to find the charge here, we first have to know what's the charge here, which means we have to know the potential and things. But to know that, we first have to combine everything down together here to find what's going on at CEQ. So let's do that. So first things first, is we want to get down to CEQ. Well, we know that C1, 2 came from 2 which were in parallel. And how do I add in parallel? just add them together. So in this case, I know that C12 is going to be equal to C1 plus C2. But at the same time, C34 came from 2, which were in parallel. I'm also going to add simply those guys together. So I'm going to get a C3 plus C4. So in this case, this works out to be 6 microfarads, and this guy works out to be 3 microfarads. So using our numbers from the previous slide. From here, we found that CEQ came from C12 and C34, which were in series, and how do we add in series? And inversely, so in this case, I get a 1 over CEQ is equal to a 1 over C12 plus a 1 over C34, which means that CEQ then is going to be equal to C12 times C34 divided by C12 plus C34. So this is going to be a 3 times a 6 divided by a 3 plus a 6. So looking at my numbers, what I find in this case then is that my equivalent capacitance is 2 microfarads. So this is my equivalent capacitance. Okay. So what did we just do? So we combine all this down here to finally find the equivalent capacitance here. Now, what else do we know? We know that the battery here is supplying an amount of 12 volts, which means that what? Since we know the 12 volts here, we now know that this is 2 microfarads. We can now find the charge on the equivalent capacitor. So let's go ahead and do that. So finally, what I can say then is that, well, the charge QEQ is then equal to CEQ times the potential from the battery, which means that this is going to be equal then to 2 microfarads times then 12 volts. That's from the battery, which is the same thing then as 24 microcoulombs. So my battery is supplying 24 microcoulombs worth of charge. Now, from here, we now go backwards. So now we say, well, we got CEQ from 2 things which came from what? 2 things which are in series, right? So this guy came from 2 things in series, and what's the same in series? Charge. So what I know then is that the charge on this guy must be exactly the same as the charge on this guy, which means that the charge on C12 is exactly the same as the charge on C34, which is exactly the same as charge QEQ. Because this came from 2 things in series, when it has to be the same in series, it's charge. So this charge here is the same as this charge and this charge. Okay? So from here, we can then say, well, charge Q12 is equal to QEQ, which was equal to 24 microcoulombs. And then Q34 is equal to QEQ, which is also equal to 24 microcoulombs. Okay? Now what? Now we know the charge here, we know the charge here, we know the capacitance here, we know the capacitance here. So what else do we know here? We also know the voltages, right? So let's find the voltages on each one. So now what I can say is that, well, the voltage V12 then is going to be equal to Q12 divided then by C12. This is my voltage. At the same time, V34 is equal to Q34 divided by C34. Now I know Q12 from here is equal to 24 microcoulombs divided by C12, where C12 is equal to 6 microfarads, which means that this is going to be equal then to 4 volts. So I have 4 volts worth of potential across capacitor C12. Right? This then is equal to 24 microcoulombs divided by C34, which had a potential of 3. So this is what? Double the size of that one, right? So that should be 28. Or sorry, 8. There you go. 8 volts. So now I have 8 volts on this one. Okay. Now at this stage, there's a nice check that you can do. Because again, what has to be true is that the voltage here plus the voltage here has to be equal to the voltage here. Since this was 12, this was 4, this was 8, I get 12 and 12, so light is great, just to make sure. So now what we know is that I have a voltage here of V12, I have a voltage here now of V34. Now from here, again, we're gonna go backwards. So now what I know is that C12 came from two capacitors which were connected how? Parallel, and what's the same in parallel? The voltage, right? Which means that the voltage here, V12, is exactly the same as the voltage here and the voltage here. So now I know that this guy has a voltage of V12, this one also has a voltage of V12. I know these things. C34 came from two capacitors which were connected how? Parallel, what's the same in parallel? The voltage, which means that the voltage here is the same as the voltage on the combined sum together. So now I know that this has a voltage of V34, this also has a voltage of V34. What's up?
Is the voltage after the capacitor? Before?
Well, it's on the capacitor.
Oh, okay.
So that is the potential drop or the potential difference between the two plates on the capacitor. So that is the potential difference across the capacitor itself. But that's a good question. So here, actually on this side has a greater potential than this side because the potential drops going across the capacitor. So this is the potential across the capacitor, meaning that the potential here and potential here are different by this amount of potential. So the point of a capacitor is to draw potential, just like a resistor. So good. So finally, our question came, what is Q4? Well, Q4 is now we know C4, we now know V34, which is the same thing as V4. So now we can finally find Q4. That was our task. So in this case, we can then say, well, finally, Q4 is equal then to C4 times then V3. Right? C4 was equal to half of the original, which was equal to half of C1, right? So that's equal to 1 microcoulomb. Am I looking at it right now? Oh, E34. I was looking at it. Okay. Speedness. So this was equal to, what are my numbers right here? So this should be 16 micro. Okay. So again, these problems are nice and kind of easy, but they are tedious at the same time. It's tedious in the fact that there's a lot of bookkeeping that goes on. There's a lot of kind of steps that go into it, but the steps are nice and easy. So again, your job is to simply first combine all this thing down into an equivalent capacitance, where again, the best thing to do is kind of draw pictures of every step that you do in between. Eventually, find your CEQ from CEQ. If they're connected in series, like this one, you can then find QEQ. From QEQ, you can then go back to here, where these now have the same charge of QEQ. Go backwards, again, always looking at what was combined together to create that particular capacitor. And then from there, you use what you know about what's the same. So again, if they're connected in parallel, the voltage is the same. If they're connected in series, then the charge is the same. So these problems are pretty easy, but kind of tedious. They can take a little bit of time to actually make it through them. What's the next one? Okay, we're not there yet. So good. So our next topic then is, well, we said that the primary purpose of a capacitor is to store energy. So let's look at how much energy is stored by a particular capacitor. So energy stored energy. So for this, let's say that here again is my battery. This guy's connected to my capacitor. So here's my top capacitor. Here's my bottom capacitor. And let's say this thing starts off initially with a bunch of charge on there. So here's my charge on here. So this has an amount of charge of, let's say, Q at this moment. Since this thing then has a charge of Q, what happens then is that this thing has now a potential difference of, let's call that simply P. Now, as we talked about yesterday, what happens then is the battery has to do work to overcome the coulombic repulsion, i.e. overcome this potential created by this particular parallel plate capacitor to store one more charge then onto the parallel plate capacitor. So let's say coming out of the battery, I have a small amount of charge moving in this direction. So let me call that simply dQ. So I have a small amount of charge coming through. And I want to know then, well, how much work does it take for me to put that dQ then onto this charge, on these charge plates? So in this case, what we need then is a differential amount of work, dQ or dW then is equal to, so remember that work is equal to the change in potential energy, which is equal to the charge times the change in potential. So in this case, I have a potential dictated by the amount of charge that's already on the plates, and I'm trying to then combine or add a small amount of charge with dQ to that. So this is the amount of work it would take to put this one little tiny charge of dQ onto this plate. But again, I'm going to do this from when it has 0 charge up to its maximum amount of charge. So what I want to do then is simply add all of these differential amounts of work together to go from the initial amount of charge, which is 0, all the way up to the final amount of charge, which is capital Q, which means we're going to do an integral. So in this case, what I want to do then is say, well, the total work then is equal to the integral over all the individual works from 0 to the finite total amount of work. But from the previous slide, this is then going to be equal to the integral of the potential integrated over the charge from the initial charge to the final charge. Now we also know that again, charge is equal to the capacitance times the potential, which means potential then is going to be equal then to the charge divided by the capacitance. So the amount of potential, which is between the two plates, at a given amount of time where this thing had an amount of charge of Q, is simply that charge divided by the overall capacitance. So this thing is going to then be equal to the integral from 0 to capital Q of then little q divided by the capacitance times the differential amount of charge. Now, does capacitance depend on charge? No, it's simply a constant, so we can pull that guy outside of the integral. This guy's going to be equal to 1 over the capacitance integral from 0 to capital charge of the charge integrated over the charge. Well, what's the integral of q dq? Q squared over 2. So finally, this is going to become equal then to the total amount of charge, or the maximum charge, divided by twice the capacitance. So what this says then is that the work done by the battery to put a charge then onto the capacitor going from 0 charge up to the maximum amount of charge Q is given by this. But as we argued yesterday, the amount of energy stored within inside of the capacitor is exactly the same amount of work that was done by the battery. Which means that the energy stored by the capacitor is equal to the work done by the battery, which is then simply equal to 1/2 the charge squared divided by the capacitance. But again, because Q is also equal to C times V, I could rewrite this in terms of the potential, for example. So I could say this is also then equal to 1/2 the capacitance squared times the potential squared divided by the capacitance, which is the same thing as 1/2 the capacitance times the potential squared. Or I could rewrite C in terms of the charge and the potential. So I could also say, well, C then is equal to the charge divided by the potential. And I could rewrite that top term then as being 1/2 Q squared divided by C then is going to be equal to 1/2 Q squared divided by Q times V. So it's 1 over the C. Which means that what? This term then cancels with this term. So this is also going to be equal then to 1/2 the charge times the potential. So ultimately, what does this say? This says that the energy stored across the battery is either equal to 1/2 the charge squared divided by the capacitance, or 1/2 the capacitance times the potential squared, or 1/2 of the charge times the potential. Either one of these are fine. They are all the same thing. So the energy stored then equal to 1/2 of Q squared over C, 1/2 of CV squared, or 1/2 of Q times V. All of these say exactly the same thing. the question then becomes, well, which one do I use? Well, I just use the one of the stuff I know. So if I know the charge and the capacitance, I would use the first one. If I know the capacitance and potential, I would use the second one. And if I know the charge and the potential, I would simply use the third. They all say exactly the same thing. There is no difference between the two. And the only difference is, what do I know versus what do I not know? That's about it. So this is the energy which is stored by the capacitor. So all this thing says is that the energy then which is stored directly either in the charge, that's what the first one says, or it's stored in the potential difference between the two plates, that's what the second one says, or the third one says that the energy is stored in both the charge and the potential. This is where all the energy is coming from. This one says it's stored in the charge. This one says it's stored in the potential. And this one says, well, hell, it's actually stored in both. So this is where the energy is being stored from. Okay. So again, the greater amount of capacitance I have, the greater amount of charge I can store, which means the greater amount of energy I can store at the same time. All right, for this. So let's do an example. So this says, in the figure below, we have a potential of a battery of 100 volts over here. Then it is attached to these three capacitors, where this one has 10 microfarads, this one is half of that, so this is then 5 microfarads, and then this one has 4 microfarads worth of capacitance. In this case, what we want to know is basically what is the charge, potential, and energy stored across all of those different capacitors. So first it wants it for capacitor 3, and then for capacitor 1, and then for capacitor 2. We're just going to do them all at the same time because that's why we have to do these numbers. So for this, I want to know what's the potential, what's the charge, and what's the energy across each one of these guys. Okay, so let's draw our picture. Okay, here is my battery connected here, and connected to here. Battery, where I get each one of these. Okay. Plus C1, plus C3, and C2. Is it okay? So we just do it exactly the same way we did the other previous two problems. So first thing we have to do is identify what's in parallel, what's in series, combine them together, eventually get to a CEQ, and then go backwards and unravel what it is that we just did. Okay. So in this problem, what's in parallel, what's in series? Good, so we know these two are in series. And then the combination of those two with C3 are then in parallel. These guys are in parallel. Good, so let's do that in stages again. So here what I'm going to do is redraw my battery, connect that guy down to then these two together. So this is going to be my C12, which is now connected in parallel then with C3. My C2. Finally, from here, I'm going to connect these guys together into my final CEQ. So this is my CEQ. And I'm going to go this way. So this is not my battery. This is my CEQ. So now what? So first thing I'm going to do is figure out what is my C12. So again, C12 can do two things which are added in series, and how do I add in series? Inversely, right? So I'm going to get a 1 over C12 is equal to 1 over C1 plus 1 over C2, which means that C12 then is going to be C1 times C2 divided by C1 plus C2. Like my numbers in this case, what I find is this works out to be 3.33 microfarads. So 3 1/3. Now from here, notice in this problem, this one is actually slightly different from the previous ones that we did because we don't actually have to go all the way down here and find QEQ. Why don't I have to do that in this case? That's Q's are equal, the voltages are equal. Because QEQ came from two things which were in parallel, again, what's the same in parallel? Eric just said the voltage, which means that the voltage across C12 is exactly the same as the voltage across C3, which is exactly the same thing as the voltage from the battery. Okay? So in this case, this is one where we don't actually have to find Q and Q first because it came from things which were in parallel. So the only time you really have to find Q and Q is when two things come from things that were in series, not from in parallel. So if CQ comes from two things in parallel, you don't have to go all the way down to here. You can actually stop here because you know the potentials have to be the same. If it came from two things which are in series, you know the charge has to be the same, which means you do have to go all the way down to here to find what is the charge. So just point that out. So okay, so at this stage, we could have actually stopped here. What we know is that the potential across here is that of the battery. This is also the potential across the battery. Okay? Now we know the potentials, we also know the equivalent capacitors. We can then find the charges. So let's do that. So here we can then say, well, we know that Q3 then is going to be equal to C3 all times the potential across the battery. So this is then going to be equal to C3, where C3 was 4, right? So this was 4 microfarads times that of the battery, which was 100 volts, which means that this is going to be equal to 400 microcoulombs. So this is my charge. And again, here we know that the potential V3 is simply that of the battery, which is equal to 100. I have to know that in a second. Now from here, let's go ahead and find the energy. We know the energy stored across here is given by one of those three things. So we can either use this as 1/2 the charge divided by charge squared divided by capacitance. We can use it as 1/2 the capacitance times the potential squared, or you do it as 1/2 the charge times the potential. Which one do you want to use in this case? Okay, so we're going to use this as Q. So this is going to be Q3 squared divided by twice of the capacitance, which is then C3. So it's going to be the same thing then as 400 microcoulombs squared divided by 2 times 4 microfarads. Look at my numbers. What I get this case then is that the energy works out to be about 0.202 joules. So this is my energy which is being stored. Okay. Now going back, again, now what we know is we know C12. We also know the potential here, which means we can also find the charge on here. So let's do that. So from here, we can then also find that the charge Q12 is then equal to the capacitance C12 times the potential across that guy, but that's simply equal to that of the battery. So it's going to be 3.33 microfarads times potential, which is simply 100 volts, which means Q12 is going to be then 333 microcoulombs. Now, I know that C12 came from two things which were in series, but what's the same in series? Q, right? So in this case, what I also know then is that Q1 is simply equal to Q12, which is equal to 333 microcoulombs. And I also know that Q2 is equal to Q12, which is equal to 333 microcoulombs. So now I know the capacitances, I know the charges. What else can I find? The potentials, right? So now I can also find what's the potential of V1. Well, V1 then is going to be equal to what? Charge Q1 divided by the capacitance C1. So it's going to be the same thing then as 333 microcoulombs divided by C1, where C1 was,
Ten.
10, thank you, divided by 10 microfarads. And it works out then to be what? 33.3 volts. V2 then is going to be also Q2 divided by C2, which is then going to be equal to 333 microcoulombs divided by, that one's 5, is that right?
I didn't get that one right now.
Okay. I think it was half the size of the other one, so I think it's 5. Good. which means it's twice the size of this one, so this should be 66.6. Okay, so that's my voltages. So finally, from these guys, we now know what's the charges, we know the capacitances, and we also know the potentials, which means to find the energy, we can use, again, any one of those three energy expressions that we want. So first thing, which one do you want to use this time?
Bottom.
The bottom one, great. So in this case, I'm going to say, well, the energy stored across the first capacitor then is simply equal to 1/2 the charge times the potential. So it's going to be then equal to 1/2 the charge, which is 333 microcoulombs, times the potential, which was equal to what? This was 33.3 volts. Plug in the numbers. What I get in this case then is, right, there it is. This works out to be something very small, 0.00554 joules. Finally, the energy stored across the second one. Let's use the other one. We haven't used that one yet. So this is 1/2 the capacitance, which in this case is C2, times the potential, which is V2 squared. So it's going to be 1/2 of 5 microfarads times the potential, which was equal to what, 66.6 volts. Watts of V squared. Look at my numbers. What I finally get in this case then is this works out to be 0.0111 joules. So yeah, these problems are nice and easy. They're just a little bit tedious because there are a lot of steps. Got to make sure we pay attention to how we got from point A to point B, because we had to go all the way in one direction and then all the way back in the other direction. Again, using what it is that we know, which is energy. Well, the charge is the same in series and potential is the same in parallel. So we'll do something slightly different than on Monday. We have a fall break, right?
2 days.
2 days. We're excited. So no class on Monday. I'll take you guys on Wednesday.